Sometimes random gives you optimal, sometimes random gives you worst case. Most of the time it's somewhere in the middle. Okay? So what we want to be worried about now is what's going on with this this idea. At the application, I'm looking at a string of bytes. Down here, I'm transferring blocks. Does anybody know why blocks? This is a bit of trivia. Okay. Hardware devices, like disk drives, are basically, other than the network, is as slow as it gets. Okay. So if we transferred a byte at a time, okay, we said, okay, you, disk drive, go off, get this byte, send it back to me. You're going to have to go down over a bus to get to your device controller. Device controller is going to have to set that up, go off, perform the operation, read the data or write the data, and come back and tell you that it's done. That's actually slower than seek time, isn't it? Because we have to send things down over the buses, we have to load the command. But it turns out that there's a lot of overhead with that. If we transfer in units of large blocks, the communications across that device interface that we saw earlier can be optimized. And then we pick a convenient block size, and it's usually a multiple of 4K. And by doing that, we can make that interface really efficient. And now that interface is to our DMA controller. And then it really is that seek time is our dominant cost. The amount of time for doing the overhead becomes, the overhead percentage of our transfer cost becomes much smaller. Okay. We were talking about this yesterday. How many people are taking, is anyone taking stats or taking stats now? Like 4 people that are taking stats right now in the other class. And one of the things that we got talking about was how to lie with statistics. All right. So we could say that our disk latency is, and give it a number, it's almost never includes the overhead for copying the data over the DMA controller back and forth. It's only inside the disk. So you could have a disk that's really, really, really efficient, that communicates across a really, really slow protocol, but will still say it operates at device speeds. And it's kind of ugly the way we lie about this stuff. But we make it simple. That is, we're not truly lying. We're telling a white lie. Because consumers are the average consumer is not like us. Okay? We are in the Illuminati. We are leaps and bounds ahead of everyone, able to understand all the nuances of quantum mechanics that go on in dealing with disk drives and the internet, right? If I were you, I'd go with that. I like to tell people when you finish with this class, get a little Illuminati patch that you put on there that says I survived 333. So there's all this little tricky little detail. We talked about this before. If we need to move the disk head, there's a read-write head at the end of that arm, and we just have to reposition it. And then, as it shows up there, all those numbers going around, those are our sector numbers within our track. This is a very simple drawing, okay? We have a great number of sectors per track on a modern drive. It's not unusual for us to have a relatively small file or data file that fits in one track. It's not all that uncommon. Compiled programs that are linked statically, like we do with XV6, tend to be quite a bit bigger than that because we have to copy whole libraries and everything in with it. But, having, 1024 or 2048 or 4096 sectors per track is not uncommon. Right? But remember, moving this arm is our dominant cost in terms of time. So, let's talk about things at the level of the disk controller. Where we talked about they have CPUs, memories, things like that. And we're going to talk about the relationship between that and the device drivers. So now we're going to talk about how do we actually manage the device? From here on out, we're not going to talk in terms of tracks and sectors hardly at all. We're going to talk about blocks. Remember we talked about the device driver layer down to the actual device is going to be a block layer. That's the interface we're going to talk about. Right? And so the question becomes, in what order or what algorithms does the device use in order to write out data? And that's important for the device driver writer because they need to send data down in an optimal form. So one of those disk blocks could actually have writes for several different files. We have to send them down in a way that helps us to optimize the interface with our device. Okay? There's different ways that we can do things. So now we think about that CPU saying, hey, I'm going to write this block. And let's just say we have a block, let's pick 4K, and say that we're going to write a 4K block for this file. We're going to assume the entire block is for our file. So we just write all of it. There's a couple of different algorithms that have, well, I say a couple. We're going to talk about a couple. There are hundreds of algorithms that have been invented over the years. Fortunately, most of them are in the dustbin of history. All right? Back in the 90s, we typically studied 15 of these and made you memorize all 15 and regurgitate them on an exam. All right? I'm just not feeling that cruel. I mean, I'm cruel, but I'm just not that cruel. We have one called shortest seek time first. Okay? And what that means is a set of requests have come down and been queued up at the disk controller level. We want to do the one that's going to have the smallest seek time. Why would we do that? It reduces latency because remember that seek time is a dominant cost. The further we have to move the arm, the more time it takes. That coasting is very expensive. That coasting step, when we accelerate the arm, then we coast to the new location. That's where most of our time is. So reducing seek is really good way to do things. But a shortest seek time first looks an awful lot like one of the scheduling algorithms that we use. Does anybody know which one that would be? Shortest job first. Shortest job first, at first glance, and shortest seek time first the same way. It's just like, this is pretty cool. All right? I will be able to do more writes per unit time, or more reads per unit time, more I/O per unit time. Except, all right, what's the problem?
Might never get to like the biggest far-away processing.
Yeah, so if we think about this now, and this is what I want you to have in the back of your head for shortest seek time first, because this is going to get ugly. Let's scale this up to 1 million tracks. Okay? And it turns out that all of our I/O is going on in the first 10,000 tracks, except that one critically important password change, which is going to have to be out in sector 900,000. If we're doing shortest seek time first, and we're keeping our queue fairly busy, this is such that we never get to that one that's 900,000 tracks away, it's as though it never gets written. It does not get persisted. And this is not good, okay, for a couple of reasons. We don't want, we've done the write, we gave it to the buffer cache, and we're like, yay, we're done. We hop in the car, we started to go home, power went out, and the buffer cache said, ha ha ha, I hadn't written to the disk yet. Bad to be you. Then we say, hey, do an F flush before you go, and that'll flush it down to the device. And the device is like going, yeah, great, it's sitting in my memory. It's not persisted yet. And if we starve it, will it ever be stored in permanent memory? This is bad, okay? Far more than bad, it's all the way up at the sucks level. Okay, SUX is just unacceptable. But starvation is a really low bar. What does it mean to starve an operation?
It'll never be called.
It'll never be executed. That's right. Okay. So it turns out that if you perform the operation 10 milliseconds before the sun goes supernova, okay, or the Vogons show up to make a highway, it turns out that you're not starving. So it's a really low bar. Okay, and that low bar is we'll eventually get around to it. It turns out if we can meet that bar, then it turns out we can improve dramatically on it on the time. So having starvation is bad, so shortest seek time first is not going to be an algorithm that we use, although the odds of us keeping a disk busy enough so that there's always at least 2 jobs in that queue, all right, one of which is a shorter seek time than the one we're trying to starve, the odds of that happening are vanishingly close to 0. But the possibility is there. Just like with shortest job first. The odds of us always having shorter jobs arrive is low. But it could happen, so we need to avoid it. So what we do now is we have a group of algorithms that are all about getting rid of the starvation problem. And there's 2 that I want to talk about. One of which is primarily how things work today, and the other one's just an interesting variation that very, very, very high performance disk drives tend to use. Okay, think disk drives that still cost, $300,000 per terabyte. So really big, really expensive hardware. Although sometimes it feels like Apple, that's what Apple put in here and they're charging me for. Okay, it doesn't actually have that type of device, so we'll see that. The book talked about an algorithm called SCAN. Okay. SCAN's job is the following: to be a fair shortest seek time first. Okay? We've recognized that shortest seek time has some optimal behavior, but it also has some very inefficient behavior. And so SCAN addresses this. Does anybody know how SCAN addresses this? It's really cool. I started off by saying an elevator algorithm. How do elevators work? They go up and down. Okay, good. We're going to go into a little bit more detail. What we're going to do is say the elevator is resting, it's not in motion. Anyone can step on that elevator at that floor and press a button to indicate either a higher or a lower floor. That will begin the elevator moving in a particular direction. So if your elevator is going up and somebody steps on and presses a lower floor, does it immediately turn around and go back to that lower floor? Does it do shortest seek time first? First it checks to see if it needs to keep moving in that direction. Okay? So SCAN does the following. It orders all of our writes by the track they have to go to. And it services all the requests in one direction before it turns around and services all the requests in the other direction using shortest seek time first. So this is shortest seek time first with a limit on when and how we can change directions. Pure shortest seek time first, we can bounce back and forth. In the elevator algorithm with SCAN, we're going to service them all in one direction, then turn around and service them all in the other direction. And we just have to have a sorted list. Okay? The devices are so slow that our local controller on our disk can do all this sorting and still be relatively unused most of the time because the disk is actually taking it. You don't move a disk in 300 disk head in 300 nanoseconds. Okay, 300 microseconds, sure, not 300 nanoseconds, and it's probably less than 300 nanoseconds to sort an incoming, do an insertion sort on an incoming piece of data. So when the data arrives, we just stick it in the request queue. And then when we're going in one direction, we start scanning. We place a pointer where there's the last place where we're in the list. It should be at one end when we turn around. And then we just start going through the list in that direction, servicing all the requests. If a request comes in that's in front of us, that is to a track we haven't gotten to yet, we insert it and we will service it when we get there. If a request comes in that's behind us, we'll get it after we turn around. Okay? Worst case, we would go from track 0, all the way to the largest track number, and then we would turn around. How many of you would like to be on an elevator that does this? Okay. The world's tallest building, I think, is still in Dubai. And you say you hop on the elevator, you get on, you go like, hey, I'm in the lobby, my room's on floor 4. You get up to floor 2, someone gets on, presses floor 1. What happens if we would have to go all the way? How many floors is that building? Like 130 or something like that? Does anyone ever use the elevator to the parking garage out here? If it moved that slowly, okay, you would probably have 2 birthdays by the time you got to the top. And then turn around and come back. We don't want to do that, so we'll service them in one direction until there are no more requests in that direction. Then we'll turn around and come back. And this is why we call it the elevator algorithm, because it works just like an elevator. It does not keep going in that direction if there's no work to do. The original one was, people will sometimes call full scan, all right, or edge-to-edge scan. Nobody uses it. We're not going to talk about it. Okay? I just don't think that's a productive use of your time. Now, there's a variation called C-scan. And I'm particularly fond with the elevator algorithms of giving elevator analogies. And C-scan has an elevator analogy. Okay, so we'll start off by saying the way it's going to work is, on this one, it's going to go from the innermost track, track 0, all the way to the outermost track. Track 1 million, let's say. Okay, and it's optimized to do this very, very quickly. It's very expensive hardware. This is at 300,000 per terabyte drive. When it gets to the end, it doesn't turn around. It resets back to track 0. It turns out for very large database systems, this can give us better performance. But it's highly specialized and very expensive because it has special hardware that you have to have. So unless you've got like a Google data center or something like that, you would not use these. Okay? Google Cloud doesn't use this. There's just not enough traffic because Google Cloud, for the most part, is doing computation. It's not transferring large volumes of data. But the database systems at the IRS, you better believe, are using these. Because they need to calculate real fast before they can ship you a penalty for your taxes, right? Okay? So, how many of you have ever heard of the movie Willy Wonka and the Chocolate Factory? Okay. Now, I haven't seen the newest one, but I did see the Disney one. And at the very end of this movie, they take Charlie onto an elevator, don't they? And then what do? They shoot it through the roof. Okay? And now in that particular movie, it's a fantasy. Okay? I can buy shooting it through the roof, but I can't buy then it magically floating without a balloon. I just don't see that. Okay? We would expect for it to go up and fall at 32 feet per second. Okay? In which case Charlie's happy, but short-lived. And that's how C-scan works. We go in one direction and we reset as fast as we can, and we can go off and do it again. And it's optimized for that. How it's optimized, it's very, very proprietary how it's done. IBM makes a lot of those drives. NCR makes some. They're just ridiculously expensive. But if your system is so busy that it's constantly doing writes, the disks really, in essence, are never idle. It's a really good way to go. Okay. The disk drivers themselves have to take into account. So this is one of the things that I didn't mention. When you're moving in a particular direction, we say a new request comes in, You have to insert it. If it's in front of the head, the direction it's moving, we insert it. Well, what if by the time you finish inserting it, you've gone by? So it turns out that the disk controllers have to be able to take into account the speed of the drive and the speed of the arm. All right? We might say if you're currently at track X and you're moving in the direction where track numbers increase, if a new track comes in and it appears to be at a higher number than X, if it's less than X plus Y, don't bother to try to schedule it. We'll get it on the next pass. Because the worst case delay would be what? What would be the worst case delay on scan? So let's say the worst case delay is going to be I'm doing a write on track 0. My next one's on track 1 million. And then my next one's on track 0. What's that delay? Is it 2 times the edge-to-edge scan? Okay. It's a relatively big number in terms of like CPU time, but it turns out it's bounded. And because it's bounded, do we have starvation? No. We also have a worst case. The absolute worst case would be we have to stop at every track along the way. That'd be the absolute worst case. Could not get any worse than that. Okay? But it's still bounded. It's still bounded. No starvation. Okay? It's really, really powerful. So, these are a form of shortest seed time first. We get fairness out of it because we service one direction, all the requests in one direction before we turn around and service all the requests in the other direction. And then we turn around and we just keep going back and forth. This should ought to be very, very efficient. Minimizes the seek